In this goal, you need to distinguish between a strong acid and a weak acid, and a strong base and a weak base. So first of all, our strong acids. So there are hundreds of weak acids and only 6 strong acids. So it's easier just to memorize the 6 strong acids, and then if it's not one of those, then you know it's a weak acid. And the weak acids, again, there's many of them, but your strong acids, there's only 6. And I use the periodic table to help me memorize it. So I go to chlorine, and it's going to be HCl, and then right below that, HBr, right below that, HI. Then I'm going to go kind of diagonally up to sulfur, and that will be H2SO4. And again, kind of diagonally to nitrogen, so that will be HNO3, nitric acid. And then I'm going to go back to chlorine, so it kind of makes a little circle, and it's HClO4. Hydrochloric acid, hydrobromic acid, hydroiodic acid, and then these ones are sulfuric, nitric, and perchloric. So if you see sulfuric, nitric, perchloric, or your binary acids, hydrochloric acid, hydrobromic acid, hydroiodic acid, these are all your strong acids. If it's anything else, then we know it's a weak acid. So if I gave you CH3COOH, and I would say strong or weak, you would say it's weak because it's not part of that 6. So these guys are strong and everything else is weak. So no matter what you have. So if I gave you NH4 plus, you would say that's weak. If I gave you HF, you would say that's weak. If I gave you HBr, well, that's on our strong list, so that would be strong. So what determines if it's strong or weak? It has to do with dissociation. Strong acids dissociate 100%. And so what that means is when you put them in water, they're going to completely separate into their ions. I'm not going to have any more of my strong acid left. It will just be ions. And so here's an example. This is a strong acid here. So this is HCl, one of our strong acids. If I had 100 molecules of my acid, and so this is at the start, I don't have any ions. At the end, you would see that they would completely break apart. So my 100 molecules, I would cut them in half basically, and I would have 100 hydrogen ions and 100 chloride ions. So because it makes so much hydrogen ion, these are called strong acids. And again, that whole list of strong acids, they will all do this. You put them in water and they will completely fall apart, and I will not have any of my original acid left. It will just be ions. Let's look at a weak acid. So this one is an example of a weak acid. Notice it's at equilibrium, where my strong acid goes to completion. So that means my weak acid can go both ways. So later on, we're going to look at the acid dissociation constant for these acids. So look at my weak acid. If I start out with 100 molecules of this, by the end, look, I only have like maybe 5 fall apart. So that means I would have 5 of this ion formed and 5 of this ion formed. So what makes a weak acid weak? It still has some hydrogen ion, but not a lot as compared to the strong acid. So again, the strong acid completely falls apart, no more acid particles left. But you can see in a weak acid, most of it is still together. So most of it is on my reactant side. So very few product side, but I still do have some hydrogen ion. So it's still classified as producing hydrogen ions, so it's a weak acid. All right, your strong bases. So when you look at your strong bases, you're going to look in the first 2 families on the periodic table, and you're going to put these metals with hydroxide. With the exception of hydrogen, which is not a metal, and also the very first 2 alkaline earth metals. They won't make strong bases, but all the rest of them will. Now, there's some of these alkali metals that are so reactive, we really don't like to work with them. They would make a strong base, but you're just not going to see them in the lab. So rubidium hydroxide, cesium hydroxide, francium hydroxide is rare and it's radioactive, so you don't want to work with that. And radium hydroxide would also kill you too. So let's not work with those. So what we end up with 6 bases that we would find in a normal chemistry laboratory, and these are the ones that are strong, okay? So anything in column 1 and column 2 put with hydroxide is strong, again, except for these first 2, all right? And then we just don't work with the bottom because they're so reactive or they are radioactive. So we're just going to avoid working with those. So we end up having 6 acids that are strong and now 6 bases that are strong. And here they are. And the reason why they are strong is they will split up 100% in water. So again, 100% dissociation. That's what makes something strong or weak. So if I put hydroxide in water, you can see that at the end, I'm not going to have any sodium hydroxide left. So it will completely break up. So I'll have 100 sodium ions and 100 hydroxide ions. And so that hydroxide, that's your base particle. And so your strong base makes a lot of hydroxide, so a lot of base. Let's look at a weak base. A weak base is anything else that's not part of this list. And let's go back to that example of ammonia, the NH3. What makes this a base? Because it doesn't have an OH. And that is because it will take a hydrogen ion from water, and what's left of water is that OH. So you can see that one of the H's here goes over to my ammonia. So I have NH4 plus and I have an OH minus. So this is my base particle. So because the ammonia takes a proton from water and it leaves a hydroxide, that's why it's a base, because it forms base. Remember the definition, at least of Arrhenius, is if you put it in water, it will form hydroxide, okay? And it's also a Bronsted-Lowry. This is also a Bronsted-Lowry conjugate base, okay? All right, so we put this in water, and again, very little of it splits up. So most of my solution will still be that NH3, that ammonia. So I'll have a little bit of each of these conjugates, but most of it is going to be that ammonia. It just stays together. So these are your strong acids and your strong bases. Remember, if they're not a part of the strong acid and strong bases list, then they're weak. Here's a diagram that again compares strong acid to weak acid. And you can see that your acid before and then your acid after, it looks very different. So it completely falls apart. Your weak acid before altogether, but notice that when we're at equilibrium, we have everything that's in the equilibrium equation present. Most of it is still the acid, the weak acid that stays together, and you do have a little bit of ion. And you actually can look and find where that hydronium ion is. So I know it's right there, and if you look really, really carefully, there's that H3O plus. So really just one molecule fell apart in this weak acid, and that proton just attached itself to a water. So again, in weak acid, you're going to see some of all of them. Mostly the weak acid is what's going to stay together, but the strong acid will completely fall apart. So in your packet, you need to diagram this. In the very first beaker, you have hydrochloric acid. So please draw some of those molecules in. And what does the hydrochloric acid do? Well, it falls apart. So I'm going to draw all the ions in, and they're all going to be separate. And so my hydrogen ion is not colored in, and then my chloride ion is colored in. So you can see that this is a strong acid because all I have are ions. This one's my weak acid. It's not a part of that strong acid list. And for this one, you're going to draw the acid staying together. So the majority of it will be together. And maybe I'll put just one separate. So I'll again have my hydrogen ion here, and then that colored one, that will be kind of the leftover when the hydrogen ion leaves. All right. So you can tell looking at a picture description, if you have just ions, well, you know it's strong. If you see that it's mostly just the acid that stayed together and it falls apart maybe a little bit, then you know you have a weak acid.